Okay, it's a pleasure to have Anna here to give us a talk. So please, Anna, you can start. Go for it.
Yeah, great. Thanks a lot. Yeah, thanks a lot for the invitation. It's the pleasure is all mine. So I'm going to share my screen with you. Can you all see that?
Yep.
Yeah, great. I'm going to fold my laptop now so that I can write on it. So you won't see me anymore, but you will see my ceiling. There it is. Okay. So, so what I'm going to tell you about today is quite graph theoretic. So I hope that's okay in this operator algebra seminar. Let me start with a little kind of graph theoretic introduction to some of this stuff. So, okay, so we're going to be talking about graph minors. So first of all, what is a graph minor? So delta here is going to denote a finite graph, and gamma will be just a graph. And we're going to say that delta is a minor of gamma if we can obtain delta from gamma by we can either contract edges or we can also delete edges, and we can delete vertices as well. Okay, so just to give you an example, let's suppose that gamma is the following graph. So let's just have some points like so. Okay, let's suppose delta is maybe this. Okay, so we can get delta from gamma by, first of all, we can contract this edge here. We can delete these red edges here, and we can delete this edge and this vertex as well. Okay, so that will give us exactly this graph delta. Okay. So another way of phrasing being a minor. So yeah, I'm going to write my notation for being a minor will be this symbol here. So if the vertex set of delta is v1 up to vn, okay, so these are the vertices, then just more formally, and also to introduce another definition, so we can say that delta is a minor of gamma if so we have some finite connected disjoint subsets which correspond to the vertex set of delta. Okay, and these are vertex subsets of the vertex set of gamma, such that there exists an edge between some vertex of vi and some vertex of vj if there's an edge in delta between the corresponding vertices vi and vj. Okay, so in other words, well, maybe I can show you on this example. So what would it give on this example? So the branch sets here, so these sets vi would be, we'd have one here, this one, this one, this one, and this one. Okay, so these would be the subsets of the vertex set of gamma, which correspond to how the vertices of delta are connected. Okay, so and the reason I said this again in this more formal way, because sometimes I might want to talk about these vi, and these are called the branch sets of delta in gamma. Okay, any questions about that definition at the moment? No? Okay, so basically we can find some subsets which are connected in the same way that the vertices of delta are inside gamma. Okay, so why are minors interesting? Well, you might all have heard about this famous theorem of Kuratowski from 1930s, which states that a graph is planar if and only if it doesn't contain the following graphs as minors. So it doesn't contain the graph K5 nor the graph K33 as a minor. Now, what are these graphs? So this is the complete graph on 5 vertices, which is like so, and this is the complete bipartite graph on 3 and 3 vertices, which is this one. Okay, so these are clearly not planar graphs, i.e. we can't draw them in the plane in a way that the none of the edges cross each other. Okay, and in fact, just not containing these as minors characterizes planar graphs. Okay. More generally, there's a theorem which isn't really connected to anything I'm going to talk about afterwards in the talk, but I just think it's a really cool theorem. So the Robertson-Seymour theorem, and this was proved fairly recently between the years 1983 and 2004. So this is a massive piece of work. This is like 20 papers, over 500 pages of work. So what they proved was that any property that passes to minors, so any graph theoretic property that passes to minors can be characterized by a finite list of what we call forbidden minors. Okay, so a bit like in this Kuratowski theorem, where we had this finite set of forbidden minors for a graph to be planar. Okay, any property that passes to minors can be characterized by just giving a finite list of graphs which you're not allowed to have as minors in graphs with that property. I'd be quite interested to see if there's any use for this theorem in something like geometric group theory. I don't think there is thus far, as far as I know, but I think that'd be quite interesting. That's the reason I mention it. And just to give more context, so I think one of the big open questions in kind of classical graph theory is a conjecture that concerns minors as well. So this is the Hadwiger conjecture made in 1943, which says that if we don't contain the complete graph on m vertices as a minor, then our chromatic number is bounded above by m. And the chromatic number is the minimal number of colors that we'd need to color our graph, the vertices of our graph, in a way that no vertices that are connected by an edge have the same color. Okay. And so what this all suggests is that when we don't contain a given graph as a minor, we should think of this as a kind of restriction on the structure of our graph. Okay, and we like that. We like restrictions. This could potentially give us a way of saying something non-trivial about the graph in question. Okay. Okay, so thus far we've just mentioned particular graphs that are not allowed to appear as minors of graphs that we're looking at. What about if we just cared about knowing that our graph doesn't contain some graph as a minor? Okay, so again, maybe this would be also a kind of restrictive property for our graph. So let's define minor exclusion. So we say that gamma is minor excluded if there exists some finite graph delta such that delta is not a minor of gamma. Okay. Now this is equivalent to there being some m such that the complete graph on m vertices is not a minor of gamma. Okay. This is because, well, obviously if there is such an m, then we have some graph, some finite graph that doesn't appear as a minor of gamma. And conversely, since any finite graph is a subgraph of a km for large enough m, we get the opposite implication as well. Okay. And minor exclusion, again, it's a restrictive property for graphs, which can give us interesting information about our graph. And just to give you an example of a more kind of coarse geometry sort of flavor, so Ostrovsky and Rosenthal, 2014, proved the following fact. If gamma is a locally finite connected graph, then Km not appearing as a minor of gamma gives us actually a quantitative bound on the asymptotic dimension of gamma. So the asymptotic dimension of gamma will in that case be less than or equal to 4 to the m minus 1. Okay, if you haven't seen asymptotic dimension before, it's a kind of coarse notion of dimension, which is useful for things like proving that your graphs nicely embed in certain Banach spaces, that kind of thing. So this is definitely something that we should be interested in. Okay, but my main aim is to talk about groups. So how can we apply these interesting concepts from graph theory in a group theoretic context? So a way that suggests itself is to look at the Cayley graphs of the groups, of course. So what is a Cayley graph? So if I have G and it's generated by some finite generating set S, then I can draw a graph that represents this group just by putting down a vertex for every group element in G and declaring that there's going to be an edge between two elements if I can connect one to the other by multiplying on the right by an element of the generating set. Okay, so these graphs capture a lot of the properties of the group. They can capture even algebraic properties, analytic properties. And so one might ask, what about properties like planarity and minor exclusion for Cayley graphs of groups? And planarity was considered actually really quite a long time ago by Maschke. Oops, no, not 1980, but 1896. So Maschke showed that every finite planar group, and I'll tell you what I mean by this in a second. Maschke showed that every finite planar group is actually a group of isometries of the sphere. Okay, so what I mean by planar group? Well, in the context of planarity, what we mean is that we admit at least one generating set with respect to which the Cayley graph is planar. Okay, because as might be quite clear, planarity will be a property that depends really on the choice of generating set for the group. So for example, if we take Z mod 5, then we could take the kind of classic generating set and get this graph, but we could also take the whole group as the generating set. And so we're going to get K5 here, which is obviously non-planar. So we really need to choose a nice generating set in order for this to work. Okay. And what are some theorems? What are some results about polarity for groups? Now, this has been studied fairly widely since this Maschke result for infinite groups. And just to give you a sample result, so the result of Ajantseva and Sherix from 2004, which says that planarity is preserved by free products. Okay, it's quite easy to convince yourself of that. If you think about a free product, you're essentially gluing your two Cayley graphs of your two groups via a kind of tree-like structure. So this is quite reasonable to expect. And there are several other people who look at polarity for infinite groups, and I think there's quite a wide range of literature on this. What about minor exclusion? So minor exclusion is a lot less in the literature, and this paper of Ostrovsky and Rosenthal, which I already mentioned, where they prove this thing about asymptotic dimension, is one of the kind of, well, this was my main reference when I was looking at this, and it's really the paper that got me thinking about this in the first place. So Ostrovsky and Rosenthal, again in 2014. So they showed that also minor exclusion is something that depends on the generating set. Okay, even for very simple groups like, I don't mean simple groups, I mean easy groups like something like Z squared. So this is, if you think of Z squared as being just a kind of grid with its classical generating set, then this is obviously going to be planar, but you can also cook up a generating set for which it's not going to be planar just by actually adding, I think, just one generator to this standard generating set, and you get something non-planar. So when we talk about minor exclusion and all these kind of properties for groups, we really need to choose, do we want to ask that there exists a generating set such that whatever property holds, or do we want to say, let's study this property that must hold for all generating sets? So we need to choose, and perhaps, well, both could perhaps lead to interesting group theoretic properties. So another thing that Ostrovsky and Rosenthal proved, so I'll just refer to this as OR from now on, was that virtually free groups are minor excluded with respect to all finite generating sets. Okay, so this is largely due to the structure of the Cayley graphs of virtually free groups. So virtually free groups have Cayley graphs that look like trees, essentially. They're kind of fattened up trees. The Cayley graphs are always quasi-asymmetric to trees. And it's actually quite easy to see conceptually why this might be the case. Okay, so for any generating set, the Cayley graph of a virtually free group will be quasi-asymmetric to a tree, so will look coarsely like a tree. And so if we think about, okay, if we have to find these branch sets that are going to give us, suppose we did have Km as a minor for any M, okay, we'd have to be able to find these branch sets, and well, where would these branch sets sit inside this Cayley graph? Well, we'd have a few over here, maybe. Then maybe we'd have a few over here, but there would be some place where these branch sets, in order for them to be connected, just as a Km, so here K5 would be, these edges that connect these branch sets would need to traverse one of these bridges. in the tree. So one of these kind of fattened up edges. Okay, so we need to have actually quite a lot of connections going across this edge in order for this to be a Km minor. And the point is that for any generating set, this blue part here, it can only be so thin. I mean, there's only a finite number of disjoint edges going across this bridge here. So we're definitely going to have a bound on the number of connections that can go across it. So we can't have a Km minor for any m that we'd like. Okay, that's essentially the reason. In that same paper, Ostrovsky and Rosenthal also proved that planarity is, not planarity, minor exclusion is also preserved under free products, just as the result for planarity of Ajantseva and Shariks. Okay, and so something that suggests itself here is the question of, is the converse true? So Ostrovsky and Rosenthal actually did ask this question. So is the converse implication true? And why might one think that it might be? Well, in kind of classical graph theory, there's so many results where an obvious necessary condition actually ends up being sufficient. You see it all over the place with things like Hall's marriage theorem and all these kind of classical graph theoretic results. It's often just a matter of spotting a clearly necessary condition and then showing that it's sufficient. So is this the case here as well? That's the question we're going to answer today. And also, I mean, it would be quite nice to have the reverse implication, just because being virtually free is already a property that admits lots of nice characterizations in geometric group theory in many different flavors. So as I mentioned, virtually free is equivalent to having your Cayley graph be quasi-symmetric to a tree. Okay, quasi-asymmetricism, as I mentioned, if you're not sure what that is, it's a kind of coarse notion of geometric equivalence. Another characterization is being finitely presented and having asymptotic dimension equal to 1. Okay, again, well, a mixture of algebraic and geometric this time. There's also various other characterizations which are maybe even algorithmic. So there's having context-free word problem. So an algorithmic characterization in terms of the word problem of the group. And all of these, many of these characterizations, so there's a million more, and many of them use something called Dunwoody's accessibility result, which we'll talk about in a second. And so, of course, it would be nice to find also characterizations which don't use this. Although I should probably say that Jago Antolin has a very nice paper which summarizes some of these characterizations and actually removes the Dunwoody's accessibility dependence from some of these results. So that's maybe something worth a look as well. Okay, so I'm going to try and answer this question, and for that we need some maybe more established concepts from geometric group theory in order to link them to this relatively new concept of minor exclusion. So let's look at ends and accessibility. So first of all, I'm going to call array just a one-way infinite proper path in my graph. Okay, so it's going off to infinity. It's a path. This is what I mean by array from now on. Okay. And two rays in a graph, I'm going to introduce an equivalence relation on rays. I'm going to say that two rays are equivalent if they stay in the same connected component of gamma once we've removed a finite set for any finite subset of gamma. Okay, maybe let me draw you a picture of what that looks like. So if I have, suppose my graph looks something like this. Okay, this is my gamma. Now, if I have two rays that are going off to infinity here, like so, here you can see that no matter what finite subset of gamma I remove, okay, I start removing some finite subsets, I remove this, okay, whatever's left of the rays still remains in the same connected component. Okay, maybe I remove a bigger piece of my graph, okay, they're still in the same connected component, they're kind of tending off to infinity in the same, along the same part of my graph, if you like. Okay, so these two rays would be equivalent. However, if I had a different ray that went off here all of a sudden, then I could disconnect that one from the other two just by removing this finite set. So those are no longer equivalent. Okay. Okay, so that's an equivalence relation on on rays and
so Anna,
yeah.
Can I ask a question? Yeah. So when you say they stay in the same component, you mean like an infinite, like you can discard infinitely many elements of your rays, right?
Yeah, exactly. Yeah. So we just care about the infinite part of the ray that remains. Yeah, that's
okay.
Right.
Yeah. Okay. All right.
Thanks. Yeah, and so we can look at the equivalence classes of rays under this equivalence relation, and these are called the ends of gamma. And these ends are quite nice, especially for groups, because the number of ends is actually a quasi-isometry invariant for groups. Okay, so we can just refer to the number of ends of a group, and I'm going to refer to that as E of G. So in particular, well, when we change the generating set for a Cayley graph, then this gives us something that's quasi-asymmetric. And so in particular, the number of ends doesn't depend on the choice of generating set, which is obviously nice. Okay, and this number of ends is actually intimately connected to the structure of the group. So Hopf in 1943, lots of old results in this talk I'm quoting. So if we have a finitely generated group, then we can kind of have a nice kind of dictionary between the number of ends and properties of the group. So first of all, the number of ends of a group can't be just anything. It actually has to be either 0, 1, 2, or infinity. And the reason for that is essentially the high degree of symmetry of the Cayley graph of a group. So once you have more than 2 ends, you can actually make infinitely many ends just by using the symmetry, so by translating and things like that, using really the group structure of your Cayley graph. So, okay, so we know that. As you might have guessed, the number of ends is 0 exactly when G is finite. So we have no ways of tending off to infinity, if you like. Now, the number of ends being 1, that's kind of the generic case. That's kind of the case where we can't really say anything specific about the structure. So yeah, nothing really to say there, but 2n's, this is equivalent to G being virtually Z, or in other words, containing a finite index subgroup that's isomorphic to Z. Okay, and what about infinitely many n's? This is a result of Stallings. From 1968. So if we have infinitely many n's, we can actually split our group up into smaller, friendlier pieces via either amalgamated free products or H&N extensions. So then our group will either split as an amalgamated free product or as an H&N extension with C finite and C kind of small enough inside A and B. Okay. Okay, so all of this put together, now if we put together this thing and this thing, what we end up getting is that, and this is what we'll actually use in this talk, is that when the number of n's is strictly greater than 1, we can decompose G as an amalgamated free product or an H&N extension. Okay, because in the case of 2n's, when G is virtually Z, we can also do this. Okay. Okay, so decompose G. Now, suppose we did have such a decomposition. So what we could ask ourselves is, of course, do A and B decompose further, right? I mean, once I've already split my G up into these nicer pieces A and B, I can ask myself, can A and B also be split up into an amalgamated free product? Or, you know, perhaps I can say that A is now some amalgamated free product of 2 other groups, okay? So continue in this way. And then you can ask yourself, well, this process, does it have to terminate at some point? Will I run out of decompositions that I can do? And this is what accessibility is all about. So we say that G is accessible if this process of decomposition that I just described terminates in a finite number of steps. Okay, so if we can finish up decomposing in a finite number of steps, we're accessible. And this result of Dunwoody, which I mentioned, so this is from 1985, tells us that finitely presented groups are accessible. This process does terminate for finally presented groups. Okay. So a note that, I mean, when we do this decomposition, okay, we can carry on going as long as the ends of the pieces that we're getting here are, the number of ends is strictly greater than 1, right? If we hit less than or equal to 1 ends, for these pieces, we have to stop, right? So that's when this tree of decompositions, if you like, will kind of terminate. So just something to bear in mind. Okay, and so what's the link with minor exclusion? Well, Ostrovsky and Rosenthal realized that ends are also linked to this property of minor exclusion. So well, we can go through the different numbers of ends and see what happens. So when we have 0 ends, of course, the Cayley graph is minor excluded for any generating set. So S is always for me a finite generating set here. So that's what I mean by any S. When the number of ends is 1, actually, in this case, we can always find an S such that Cayley graph is not minor excluded. Okay. Then for two ends, we know that our group is virtually Z, so it essentially looks like a lot like a line, like a thick line. And as you can imagine, you can't fit any minor that you'd like into a thick line, just for the same reason that as for virtually free groups. So this will be minor excluded for any choice of generating set. Of course, we can ask ourselves, what about infinitely many ends? So Ostrovsky and Rosenthal didn't say anything about infinitely many ends, and we're going to say something about that in a second. Okay, any questions about that at all? No? Okay.
So just to make sure I understand this notion of ends. So the free group has uncountably many ends. Is it correct?
The free group has infinitely many ends. Yeah.
Okay.
Yeah.
Right.
That's right. Yeah, you can kind of see it for a free group. I mean, you know, if you have your Cayley graph of a free group, it's a tree, right? And okay, you can remove just a vertex to disconnect it into 4 parts. Then you can remove these parts to get even more parts, and you can carry on going this way.
Yeah,
to
right.
get as many ends as you like. Yeah. Okay. Right. So now, okay, let's talk about characterizing virtually free groups. So, in fact, the answer to this question that Ostrovsky and Rosenthal asked in 2014 is positive. We can characterize virtually free groups using minor exclusions. So we can show that if G is a finitely generated group, this is minor excluded with respect to any generating set, and G is virtually free. Okay, and so putting that together with the result of Ostrovsky and Rosenthal, we get a characterization. Let me tell you a little bit about the proof. So nothing too difficult. So first of all, let's see that this is true when G is accessible. Okay, so we can actually do essentially the full proof of this. So when G is accessible, so as I said, that means we can start decomposing our group if it has more than one end, and we're going to finish that process off in a finite number of steps. So what this means in the language of Basset theory is that G is the fundamental group of a finite graph of groups, finite edge groups, and vertex groups with number of ends being at most 1. Now, if you're not sure what that means, what I mean is just essentially when we reach the bottom of this decomposition tree, okay, when we reach the pieces at the end that we can no longer decompose, so the ends with the groups with which this must finish must have less than or equal to 1 end, right? Otherwise we could keep going. So this is just a fancy way of phrasing that, really. Okay, but now could we have, at the end of this decomposition, could we have pieces that actually have exactly 1 end? The answer is no, right? Because, well, here, I'm going to call this star. here we said that for groups with one end, there's always a generating set such that the Cayley graph is not minor excluded, right? So by star, we actually cannot have subgroups with the number of ends being equal to 1, because if we did, suppose we did have some subgroup, so all of these, right, all of these pieces that we get out at the end of this decomposition, they're all subgroups, right? So if we did have one of these subgroups that had exactly one end, then we could find a generating set for that subgroup, which, with respect to which its Cayley graph was not minor excluded. And then I could include that generating set for the subgroup in a generating set for my whole group. Okay, and what that would do is it would give me a copy of the Cayley graph of that subgroup inside the Cayley graph of my big group as a subgraph. So since my group is supposed to be minor excluded with respect to any generating set, this shouldn't be possible, right? So we actually cannot have any groups with exactly one end. And so all vertex groups must be finite. In other words, they must have 0 ends, they must be finite. And this is actually equivalent to the group being virtually free. So G is virtually free by a result of Harris, Kuratowski, and Solitar from 1973. Okay, this is a result that predates the Dunwoody result, so it doesn't rely on Dunwoody's accessibility. Okay, so we haven't cheated there in any way. Okay, and you can see this is very simple, right? So okay, so now how do we do the general case? So we've seen that for accessible groups, this is true. Now we can actually show that minor exclusion actually implies accessibility. So minor exclusion with respect to any generating set actually implies that G is accessible. Let me give you a little sketch of that. So, and this mainly relies on a very nice result of Thomason and Verse from 1991. If I actually give a graph theoretic characterization of accessibility. So if we have some generating set S of G, what Thomason and Verse showed is that G is not accessible. And in this paper, they actually introduce the notion of accessibility for general, I think, vertex transitive graphs. So something that can also be looked at in a wider context. And so what they prove is that G is not accessible if and only if for any m greater than 0, the Cayley graph has what I'm going to call a thin end. I'm going to tell you what that means in a second. It's largely what you imagine it to be. Has a thin end such that the maximal number of disjoint rays in this end is at least m. Okay, so it's on the one hand it's a thin end, on the other hand it has a lot of disjoint rays inside it. So what do I mean by a thin end? Well, let's imagine again. Let's suppose that's our graph. So suppose we're looking at this end. Let's call it omega. So omega is thin if we can slice up this end into subsets. Okay, I'm going to call them x0, x1, x2, etc., which are disjoint and which have the following properties. So for all I would like xi plus 1 to be inside the connected component of my graph once I've taken away the previous xi. So the connected component containing the end that I'm looking at. Sorry. So yeah, maybe let's define. So let's call gamma I the connected component of my graph. Once I've taken away the subset xi, that contains my end omega. So what I'd like is for these xi's to be inside gamma I. The next xi plus 1, I'd like it to be inside gamma I. And I'd also like gamma I plus 1 to be inside gamma I. Okay, so let me maybe just give you an example. So if I'm looking at x1, what's gamma 1 going to be? Well, once I take away x1, what have I got left? What's the connected component of the Cayley graph minus x1 that contains omega? It's this bit, right? So, so that's my gamma I in this case. And so this is just giving me a condition. I mean, it's essentially saying that my xi's really do look like this. They're really kind of slicing up this end as we go along, as we go along this end omega. Okay. So this picture, what I'm saying is this picture is really representative. And we say that omega is thin if we can actually take these xi to be bounded in cardinality, or maybe even equal in cardinality to k for all I. Okay, so essentially it means that we're not getting, we're getting really something like this, where we can slice up into pieces that are kind of equal size, and we're not getting something like this, okay, where this end, if I start doing a similar process here, if I start defining these sets, at some point I'm not going to be able to disconnect the rest of this end here from the rest of the graph using something small, right? So my end isn't kind of getting fatter and fatter in some sense, it's thin, okay? So using this characterization of Thomson inverse, if we suppose that our graph is minor excluded with respect to NES, suppose that our graph wasn't accessible. So then this characterization provides us with at least m disjoint rays in a given end, right? And we can actually use these m disjoint rays to build a minor. So we can then use the m rays to construct a km as a minor inside our Cayley graph. Except we have to modify the generating set slightly. We can't just take the usual generating set that we already fixed here, which is S. We actually have to enlarge it a little bit, but we enlarge it in a uniform way that works for any m. Okay, we actually have to take we actually have to include all squares of generators and all cubes of sorry, not all squares, we have to include as edges also anything that is connected by at most 2 edges and at most 3 edges. Okay, but this allows us to construct a Km minor inside this Cayley graph, and so that gives us a contradiction because we suppose that our Cayley graph was always minor excluded regardless of the generating set. Okay, so that's the general idea of the proof. And so this doesn't, as I said, use Dunwoody's accessibility, so that's nice. It also helps us answer what happens for infinitely many ends. So this tells us also that, in particular, that we do have some group and a generating set of that group such that the number of n's is infinite and the Cayley graph is not minor excluded. Okay, so in some sense we see a little bit of what happens for infinitely many n's as well. And I'd just like to finish with a question. I think one of the open questions to do with minor exclusion in groups now remains as follows. So can we characterize groups which admit at least one generating set with respect to which they're minor excluded? So what if there exists some generating set such that the Cayley graph is minor excluded? What does this imply for the group? Can we find a nice group theoretic characterization of this property? And there's some, there's some properties that we already know. I guess the interesting thing would be to really characterize what groups these are. There's some consequences of this that we do know. So, for example, a recent result of Bonamy and some collaborators, which I'm not going to list, quite a lot of them, they proved that this actually implies that the asymptotic dimension of such a group would have to be bounded above by 2. So that excludes, obviously, many, many groups. There's also restrictions that you can think of on subgroups of such groups. So you can't have anything that isn't minor excluded as a subgroup. You can't even have something like z squared crossed with some finite group. This would already preclude the existence of such a generating set. And obviously this class of groups would have to be closed under free products, and they would have to contain virtually free groups and planar groups and things like that. So I think that would be quite an interesting avenue of research in the future. Okay, I think I'll stop there. Thanks.
Thanks for your talk. Do you have any questions, Joanna?
Yeah, I have a question. So can we say something interesting about virtually abelian groups and minor exclusion?
Virtually abelian groups.
It's probably a too broad question. I don't know if it's.
Yeah, I mean, obviously the virtually Z ones will be minor excluded with respect to any generating set, and then as soon as you have as soon as you have a copy of Z squared, then you're going to have at least some generating set with respect to which it's not going to be minor excluded, but yeah, I mean, I guess it's not very, I mean, and then I think once you have a Z cubed, then you're not minor excluded with respect to any generating set, I think. Yeah, exactly. So I think, somehow something happens in between, Z squared and Z cubed. Something. No, I guess, yeah. I mean, even if you have Z squared, and as I said, even if you have something like Z squared crossed with something small abelian, like some finite abelian group, then already you will not be minor excluded with respect to any generating sets. So, yeah. But yeah, so somehow it's hard to draw the line somewhere, if you see what I mean. I mean, Z squared still has the generating set, which with respect to which it's minor excluded, but z squared crossed with something small already doesn't. So it's kind of strange in that way.
Do you have any other questions?
I have another question. Sorry. So can you go back to your, I think the result of Ostrowski and Rosenthal? So
Which
so the very first one. So the statement was what? So if they
about asymptotic dimension, is that right?
Yes.
Yes.
So I think it's stronger. They proved something stronger than that, right? Didn't they show that Aswad negative dimension is?
Yeah, they did. Yeah, sorry, they actually
Finite.
showed Aswad negative dimension is finite. Yeah, and this is just a consequence of that. Yeah.
And so if if a group is minor excluded for every finite generating set, then it has to be virtually free, right? Okay, so my question is the following then. So when you have Aswad finite Aswad negative dimension, then every snowflake of the metric space embeds bilipschisly into let's say a Hilbert space. So would it be true that if every snowflake of a finitely generated group bilipschisly embeds into a Hilbert space, does it imply that the group has to be virtually free? Can you prove this under this weaker? I mean, because so what I'm asking is to prove virtual freeness under a weaker assumption than.
Oh, that's a really interesting question. Yeah, I'm not sure. Yeah, I never thought of that. I don't know how much weaker the snowflaking thing is. Yeah, that's a really nice question. Yeah.
So yeah, the idea is to replace this graph theoretical condition by a purely metric condition, but that has to be. And here, so since the geometry is independent on the generating set, then you just have a condition on the group that would imply to be virtually free.
Yeah, that would be a really nice characterization.
I'm thinking about that because yeah, because there is this conjecture of Tessera, the Cornelian valet, which asks whether if a group bilipschisly embed into a Hilbert space, does it have to be virtually abelian? So it's kind of well, I guess it's in the same spirit, kind of. You know something about embeddability of your group into Hilbert space, and you want to deduce something about the algebraic structure. So maybe here there could be a positive result, but instead of virtually abelian, you have virtually free.
That would be really nice. Yeah, that's a really nice question. Thanks.
But it might be. I mean, there might be a counter example. It might be wrong, but that I don't know. Yeah, I was wondering if you thought about that or not. But.
Yeah, I haven't thought about it. No, that's a really nice question. I will think about it.
It seems natural. I mean, to ask this, but maybe it's too naive. I don't know. I don't have any more.
You have another
question? No, thank you. Thanks for the talk, Anna. It was great.
Anyone else? I see Rufus unmuted himself. So no, okay. Okay, let me stop the